I want to make a video with some very clear explanations about the topic of light travel and the speed of light itself, and more specifically the boundaries of trying to get to the speed of light, because I'm kind of tired of hearing people constantly repeat the same explanations over and over that don't seem to make any sense. Like that it takes an infinite amount of energy to get to the speed of light, or uh, the idea that if you traveled at 1 g, the speed of 1 g, for 6 months and then came back to Earth, it would be thousands of years into the future. So, none of those main things that these guys explain don't ever make any sense to me. So I'm making a short video here with my explanations that make more sense to me. So first thing I'm going to go over is why we cannot reach the speed of light using propellant and rocket ship propellant and power, is because whatever departing speed of the propellant that you're using has a limited departing speed of the speed of light of whatever propellant you use. Even if you had a laser, a beam of light as your propellant, like if this laser here was your propellant, even if you had this beam of light to push you along, you'd still be limited by the departing speed of the beam itself, because you can't go any faster in the other direction than the speed of your propellant that's leaving. If the propellant's going 186,000 miles a second this way, you're going to go probably slightly less than 186,000 miles a second in this direction because of your inertia. Because of your mass, you can't go any faster than the propellant that's leaving, and because of your mass, your inertia, you can't go any faster than slightly less than the speed of the propellant that's leaving. So that's the reason why we cannot push ourselves to the speed of light and beyond, because we have no propellant that we can shoot away from us any faster than light speed to go any faster in the other direction. But we do have another way of gaining velocity without using propellant, and that's with these maglev trains. And the way they get their velocity is by a traveling magnetic field. As the magnetic field is moving along, the train gets pulled by it. So at least this is a way we can gain velocity without having to use propellant, and our limitation is just how fast we can make a magnetic field travel. And if you study light waves, electromagnetic waves, you'll learn that light waves are just pulsating electric and magnetic fields that are coming from every light source in the universe, in the sky, like a star. And the way the waves propagate into space is you have an electric field that is collapsing, and a magnetic field then expands. As the magnetic field collapses, then the electric field expands. So you get this pulsating magnetic and electric fields that are traveling away from every source of light in the universe. And these are pulsating electromagnetic fields that overlap each other, that are non-polarized. Light that you look at when you look at a star is non-polarized light. They're overlapping electric and magnetic fields that are pulsating off of each other. That's how they propagate into space. But if you use certain optic tools with electromagnetic waves, you can take non-polarized light and you can turn it into polarized light. And you can take polarized light and turn that into circular polarized light. And when you have circular polarized light, you have an electric and magnetic fields that are rotating. They're not expanding and collapsing anymore. They rotate as they travel through space. So if we can figure out a way to use a rotating, traveling electromagnetic fields to gain velocity, just like our maglev trains, then that'll give us at least some sort of method of gaining velocity or acceleration using light itself, or electromagnetic radiation. Now, before I go into some of the details on more of the boundaries that I think we have when it comes to particle accelerators and using a beam of light to push us through space, I want to go over how time dilation originally came into concept by Einstein, by his thought experiment.
One evening in the spring of 1905, Albert Einstein, then a mere patent clerk in Bern, after trudging through his day's work, decided to board a tramcar on his way home. Einstein would often wrap up his work as soon as possible to contemplate the truths of the universe in his free time. It was one of these thought experiments he devised on that tramcar that revolutionized modern physics forever. While receding away from the Zeitglocke clock tower, Einstein imagined what would happen if the tramcar were receding at the speed of light. He realized that if he were to travel at 186,000 miles per second, the clock's hands would appear to completely freeze. At the same time, Einstein knew that, back at the clock tower, the hands would tick along at their normal pace. For Einstein, time had slowed down. This thought blew his mind.
So, according to that little cartoon clip we just saw, Einstein realized that the faster you move through space, the slower you move through time, or at least that's what he thought. And I have a different explanation that has to do with the rate of time change based on your velocity when you're going towards something or when you're traveling away from something. You see, if we truly believe that time slows down everywhere around us as we accelerate through space, then that means that anything that we travel towards will slow down in time, as well as anything we travel away from will slow down in time. But that doesn't make any sense if you were able to go faster than light and go towards, say, Andromeda, our neighboring galaxy, because we're looking at Andromeda into the past. And if time would slow down everywhere around us, then that means that as we travel towards Andromeda, the time would slow down and come to a freeze, and then what would happen if we get closer and closer to Andromeda, if time is frozen for it in front of us? That would mean that we're going into the past when we go towards Andromeda, or we're going into the past whenever we travel towards something, and that's not what happens. What happens when we travel towards something is the frequency of the light that we're looking at when we're traveling towards something speeds up in its frequency. And when that happens, the time rate will not slow down for whatever you're looking at when you're going towards something. If the frequency increases for whatever it is you're traveling towards, then that means that the time rate will increase. When you travel away from something and the frequency decreases, the frequency of the light that you're looking at when you're traveling away from something decreases, that means that the time rate for that object will slow down. It's not the speed of the light itself, it's not the velocity or the traveling speed of the light itself, it's the rate of time that you're seeing the light flicker at. And I do believe that when you go at the speed of light, then the time will freeze, the rate of time will freeze for the light that you're looking at behind you. And if you go faster than light, then the time rate will actually reverse its direction. And it'll look like whatever you're traveling away from is going in reverse time direction, or it looks like it's going backwards through time into the past. And that makes more sense. If you travel towards Andromeda faster than the speed of light, then that means that you would see the time rate increase like it's fast forwarding through time. And when you get right up on it, then you'll see what it looks like at the present time. And everything that you're traveling away towards will have gone into the past the same amount that Basically, whatever amount of distance you travel, then the objects that you're ever traveling towards or away from will change their time rate relative to whatever distance and speed you've traveled. If you traveled 2 million light years away from Earth, then you'll see Earth what it looked like 2 million years into the past. So time will have reversed its direction 2 million years all the way into the past if you've traveled that far. Same thing if you travel towards something, you'll see it fast forward through time 2 million years into the future. And when you get right up on it, you'll see what it looks like at the present time. So that makes more sense when it comes to time dilation versus the explanations that we hear all the time that you would be coming back thousands of years into the future. That makes no sense whatsoever. But anyway, moving along, I wanted to explain why we can't make particle accelerators go faster than light speed, because we're actually making the particles travel in a circle, and as we make something travel in a circle near the speed of light in such a short distance that it's traveling, then the particle itself actually gets stretched around the circle of the particle accelerator. And the reason it can't go any faster is because if you add more energy, the particle is basically running into the back of itself. It's running into the tail of itself that it's leaving behind as it travels in a circle. So that's the reason why you add more energy to a particle or a proton as it goes in a circle in a particle accelerator. The reason it gets heavier and can't go any faster than light speed as it goes in a circle is because it's stretched all the way around the circle and it's running into the back of itself. So the more energy you add to the particle in the particle accelerator as it gets close to the speed of light makes it heavier because it's basically just pushing on itself. And that's why it gets heavier. Same thing why we look at quasars in the distant universe. When they're going around a black hole, the collapsing black hole, as the black hole pulls it smaller in a smaller circle, the particle actually begins to run into the back of itself and it starts to rub against its tail as it goes down the collapsing black hole's gravity pull. And that's why we see light coming off of quasars, because these particles are basically causing so much heat as they rub against themselves while they travel down in this spiral formation in the collapsing black hole. Because the black hole is basically an object that's so heavy that it's constantly collapsing itself into a smaller and smaller size, never reaching a smallest point, because there's no smallest point possible to reach in the measurements of the dimensions that we live in. Ergo, we have a collapsing object, an object that's so heavy it's constantly crushing itself into a smaller and smaller size, and its gravitational pull brings objects with it. So basically, if you try to run into a black hole, you couldn't hit it. You couldn't run into it. You would always go past it and get pulled into a circle down into the black hole. You could never actually run into a black hole like if it was a planetary object. It's an object that's so small and constantly getting smaller, there's no way you could collide with it. So, and that's the reason why particle accelerators have the limitations that they have. And another limitation that we have for trying to reach light speed is by using a powerful laser to move a rocket or spaceship away from the planet. And this has its limitations by the arrival time of the light beam that you're using to gain acceleration with. There's no speed that the light beam could arrive that's faster than light speed, so you can't be pushed any faster than the speed of the light beam that's arriving. So you have the same situation as you have up here, except in reverse. Instead of a limited departing speed, you have a limited arrival time. And if you even get close to the speed of light, then that means that the time rate for whatever home planet is supplying the laser acceleration method here, the time rate for that home planet would slow down and almost come to a stop when you get close to the speed of light. That means if you get close to the speed of light, the time rate if you make the time rate go any slower than absolute zero, then that means that you wouldn't have any laser propulsion anymore. So you're limited by the time rate here, and you're limited by the light beam's arrival time. So I came up with a concept that actually cancels out all these physical boundaries that we have for trying to reach the speed of light and beyond, and that's by using an electromagnetic wave as your traveling magnetic field to gain acceleration or gaining velocity. And the only way that you could actually do this is by having a source of light or a source of electromagnetic radiation that you would capture and then redirect back to the source. Because no matter what speed you are moving at, light is always going to arrive at 186,000 miles a second faster than you are, no matter how fast you are going. So if you're going 3 times the speed of light in this direction, that means that the light that's arriving at you is going to be going 4 times the speed of light to reach you. If you're going 100 times the speed of light in this direction, that means the light that's chasing you is going to be going 101 times the speed of light to catch you. No matter how fast you go, light is always going 1 times the speed of light faster than you are. So if you can use a light source that is always going to be going 1 times the speed of light faster than you, and you use that for your propulsion, then that means there's no limit to how fast you can make yourself travel, because you can always go faster and faster, because the light that's arriving and the light that's departing from you is always going to be going 1 times the speed of light faster than you, no matter how fast you accelerate yourself. So if you have a source of light, like a star in the night sky, that you can capture, redirect back to the source, you can then insert yourself into the redirected beam of light, and then use that as your propulsion to go as fast as you want towards any source of light in the night sky. That would give an unlimited velocity speed that you could gain based on this method, if you can figure out a way to take electromagnetic waves, turn them into circular polarized light, and then use those rotating electric and magnetic fields to then gain acceleration. And I think that the way that you can control your acceleration and your deacceleration is by using wave strengthening and wave weakening effects when it comes to the waves when they overlap each other. When you have the same source of light that starts to overlap itself, then you have cancellation effects and you have amplifying effects of whatever light wave is overlapping itself. And by controlling the waves that cancel or the waves that amplify themselves, you can use that as a way of controlling your velocity. Like if you can make the waves amplify that you're redirecting, then you can use that to gain velocity. If you can use the cancellation effect of light waves, you can use that to decrease your velocity. And that would be a way of traveling, using any source of light in the night sky to travel to the speed of light and beyond. If there's a physical way of being able to build a machine that can actually control light in this fashion. I don't have any way to prove it yet, but I do strongly believe that this is a practical and real method of gaining velocity to the speed of light and beyond, because by using this as your source of acceleration, it cancels out all the problems that I went over up here. The departing speed, the arrival time, the time rate change limitations that you have. We're trying to go faster than the speed of light and having time slow down and come to a stop. I mean, this, by controlling light in this fashion, you have no time dilation boundary, you have no arrival time or departing speed of light boundary, because you're using the source of light itself to travel, and no matter how fast you go, the light always has to arrive at you and depart from you at the speed of light, or 1 times the speed of light faster than you. So if you're using that light to gain velocity, then there's no limit to how fast you can make yourself move, because these light beams are always going to be going 1 times the speed of light faster than you. So hopefully that makes sense to whoever's watching this, because it makes a lot more sense to me than the typical explanations that get said over and over and over again about why you can't reach the speed of light and what time dilation is, and you know what, and for people who don't believe that you can get to the speed of light and beyond, because I do believe that you can get to the speed of light and beyond, but it takes a certain ingenuity and practical method like I came up with here. You need to be able to use light itself and be able to capture and redirect it and use it as your accelerator, because there's no way to reach the speed of light using propellant or using a beam of light that you shoot at a ship. Will not reach the speed of light either, or go faster than the speed of light. And also why particle accelerators can't go any faster than the speed of light, because they've got a limited distance that they travel in a circle. Ergo, they're going to always run into the back of themselves when you try to accelerate them to the speed of light. So basically, if you had a particle accelerator that was bigger than 186,000 miles, you could, like if you had it 300,000 miles, then maybe you can make it go faster than the speed of light, because then it wouldn't be running into the back of itself, because there wouldn't be this limited distance that we have with our accelerators that we test accelerating protons with here on Earth. So okay, that's where I'm going to end it. And those are my practical explanations of the boundaries and the limitations we have on light travel, and my explanations on getting to the speed of light and beyond.